Hello, this is Dr. Simon Romero, and I'm here to give you the first video of our series of video tutorials, and this one is going to be about vectors. This is section 12.2, and the name is vectors. In this section we're going to see the definition of a vector, components of a vector, vector addition and scalar multiplication, geometry of a vector, standard basis, and unit vectors. These things are the practice problems. I suggest you to do them all. You don't have to give them back to me, but if you have any questions, these problems are a good way to point where do you have problems. Let me start with the type of quantities. You have two types of quantities. You have scalar and vectorial quantities. Scalar quantities are quantities described by numbers like time, mass, and distance. However, in real life, we actually need other kind of quantities that are called vectorial quantities. The vectorial quantities are described by a number, magnitude, and in most cases a direction, like displacement, velocity, acceleration, and force. What a vector is a mathematical expression of a vectorial quantity. Geometric representations of vectors. Both in R2 or R3, the plane or the space, we represent a vector B as a direct segment, an arrow, joining 2 points. We can represent the vector B joining P to Q also as PQ with an arrow over the top. This is like a geometric description of what we are saying right now. Let me just put a highlighter. And here is what we're talking about geometrically. The length of the line segment represents the magnitude of PQ. So this length over here represents its magnitude. And the magnitude of PQ is denoted by these double bars, PQ. We use double bars to distinguish between absolute values for numbers. Vectors and components. Geometrically, the vector is represented by an arrow. Algebraically, a vector B in R3 is given by 3 components. A vector B is represented by 3 real numbers, B1, B2, and B3. These numbers are called components and denote the assigned displacement in each one of the directions of the coordinate axis. We write B as B1, B2, and B3. Notice that in this particular drawing, B1 denotes how much we move in the x direction, B2 is how much we move in the y direction, and B3 denotes how much we move in the C direction. We use these pointy brackets to distinguish between vectors and points. A vector joining 2 points. Given the coordinates of the tip and the tail, we can determine the components of a vector joining them. So for example, if the T here is P and the tip is Q and the tail is P, then the thing that we do is the vector PQ will denote the x coordinate x2 of the tail of the tip minus the tail. We do the same for the y coordinates and we do the same for the c coordinates. In other words, tip minus tail. As the zero vector and equality of vectors. The zero vector is called, the vector 0, 0, 0, is called the zero vector and is denoted by 0 with an arrow over top. The zero vector has zero magnitude and no direction. The zero vector is the only vector that has no direction. Equality of vectors. 2 vectors are equal if they are equal component-wise. What it means is that 2 vectors are going to be equal. You have the same vector no matter where do you place them. Vectors are independent from where you place the vector. So in this case, these 2 vectors are equal. Vector addition. If you have B equal to B1, B2, and B3, and W equal to W1, W2, W3, then B plus W is going to be the addition of each one of the corresponding components. In this case, here is the vector B and its components, and then the thing that we're going to do is we're going to add to each one of the components of W, that is equivalent to putting the vector W the tail of the vector W in the tip of the vector B. So here it is the vector W and its components. Then the resulting vector B plus W is going to be the vector that joins the tail of B with the tip of W. This proves, and then if you do it the other way around, like this proves geometrically that b plus w is equal to w plus b. Scalar multiplication. If you have a vector b1, b2, b3 and c is a real number or a scalar, then c times the vector b is just multiplying c to each one of the components, and what it results geometrically is if you have the vector b and you multiply it, say, by 2, then you obtain a vector that is twice the size of b, but it has the same direction. Now, if you multiply by a negative number, let's say 1/2, negative 1/2, this one has half of the magnitude of b and is in the direction opposite to b. This is going to become important later on in this section. These are the comparison of the three vectors that we have. Parallel vectors. If two vectors non-zero have the same direction or opposite directions, we say that they are parallel. Two vectors b and w are parallel if there is a non-zero scalar such that you can obtain one by multiplying to the other one. In other words, it's the same as saying that have the same direction or opposite directions. Vector subtraction. If you have a b and w, two vectors, then b minus w is technically just going to be b plus minus w. So the thing that you're going to obtain is you are just subtracting the corresponding components. In other words, you have something like this, and b minus w will be this one over here. Why? Because you can see it as the sum of b minus w or the sum of minus w plus b. The standard basis. The following vectors from the standard basis form the standard basis in the space. So they are vectors that move one unit in the particular direction of the coordinate axis. Oops, I think that I have to compress a little bit that last line. So here we have them like just a picture of what are the unit vectors. They move one in the x-axis, one in the y-axis, the j one, and k move one in the z-axis. The hats are used to distinguish these special vectors from the rest. Linear combination and standard basis. A vector, three vectors given three vectors w1, w2, and w3. The vector b is a linear combination of w1, w2, over w3 if they are three scalars such that b is equal to a w1 plus b w2 plus c w3. In other words, we're saying that b can be seen as a sum of scale versions of w1, w2, and w3. One theorem that we have is that every vector b in R3 is a linear combination of the vectors I, j, and k. So in other words, we can just scale I, j, and k to obtain the vector b after adding them together. And the proof is pretty easy. Let's start with an arbitrary vector b1, b2, b3. Notice that I'm taking a generic vector, so we will prove it no matter what b1, b2, and b3 are. Then b is equal to b1, b2, b3, the vector b is equal to b1, b2, b3, but that happens to be the sum of b1, 0, 0, 0, b2, 0, and 0, 0, b3. Those three vectors add up to b. But that, taking the scalars out, is the same as multiplying the scalar b1 to the vector 1, 0, 0, multiplying the scalar b2 to the vector 0, 1, 0, and multiplying the scalar b3 by the vector 0, 0, 1. That happens to be b1i plus b2j plus b3k. Notice that this gives you another way to represent vectors. You can represent vectors by brackets, or you can represent vectors by its linear combination with respect to the vectors I, j, and k. Notice that these two are pretty much the same because we're talking about the same components. Magnitude and components. Using the distance formula, we can compute the magnitude of a vector by its components. Since the magnitude is just the distance from tip to tail, we can use that distance formula, and we get that the magnitude of v is just squaring the components of the vector and then taking the square roots. There are two properties of the magnitude. One is that the magnitude of the sum is less or equal than the sum of the magnitudes. That's called the triangle inequality. And the other one, that it says that if you multiply a scale version of b is going to be the absolute value of the scalar times the magnitude of b. Unit vectors. A unit vector is a vector of magnitude equal to 1. If you want to compute a unit vector in the direction of v, you can just multiply by 1 over the magnitude of v. And that gives you a unit vector in the direction of v. Why? Let me prove it. Since the scalar 1 over v is positive, v and u have the same direction. So we only need to prove that the magnitude of u is 1. The magnitude of u is the magnitude of 1 over magnitude of v times v. But that's equal, because of the properties of the magnitude, to 1 over the magnitude of v absolute value times v. But the scalar 1 over v is positive, so it ends up being magnitude of v over magnitude of v. That gives you the scalar. So that means that this vector u, that means that the magnitude of u is 1, so it means that the vector u is a unit vector. Let me give you an example. So find a vector in the opposite direction of the vector v equal to 2i plus 3j minus 1 half k with magnitude 3. The first thing that we do is we find a unit vector in the direction of v. So since this is the magnitude of v, then u, the unit vector in the direction of v, is going to be 1 over the magnitude times the original vector. That gives you this vector over here. Now if we multiply u by the scalar minus 3, we flip the direction because of the minus, and we'll multiply the magnitude of u, that is 1 by 3. Notice that I forgot my parenthesis here. I will put it right now because of the minus, and then we'll multiply by the magnitude of u, that is 3. So the vector that we're looking for is 3. Let me just put it right here. Is minus 3 times u. Minus 3 because it's magnitude 3, the one that we want, and the minus is because we're flipping direction. So minus 3 times that, and that gives you the vector that we're looking for. With this, we finish this tutorial about vectors. If you have any questions, you can come and ask me. Remember that you can fast forward and pause anytime in this video, so you can kind of like go at your own pace. Well, thank you very much, and I will see you later.